Okay. So Angelia, shall we start now?
Yeah.
Okay, good. So let's get started. Okay, so good morning, good afternoon, or good evening, everyone. So welcome to this season finale of this One World Signal Processing Seminars. So today it is our pleasure to have Professor Angelia Nedich from Arizona State University to share her research about distributed optimizations. So let me first introduce the speaker in case you don't know her already. So Angelia, actually, Professor Angelia Nedich holds a PhD degree from actually both Moscow State University and MIT. So before joining the University of Illinois in Urbana-Champaign as an assistant professor, associate professor, and then professor. So she is currently at Arizona State University as a professor in electrical engineering. So she has received many awards. She has, for example, a Best Paper Award at the Winter Simulation Conference and a Best Paper Award in the International Conference on Modeling and Optimizations. So perhaps the best, Angelia is more famous for her work on distributed optimizations. For many one of us has read her work on distributed optimizations in transitions on automatic control, written with Professor ASU Stegler. This is really a pioneering work on building up these decentralized optimization tools. So today she is going to share with us her new findings about distributed optimization in networks as well. So please join me in welcoming Professor Angelia Nedich. So the floor is yours.
Oh, thank you. I'm sorry. So actually, I'm very happy to be here, and I'm excited actually because I see a big number and scared a little bit, but that's okay. So I'll talk about distributed algorithms, but I actually will like to give you more of a story how we started and how we got improving and changing and kind of making algorithms better in sense of some of the deficiencies that we initially had. So it's more of a story about what we have been doing for probably about 10 years. And with that, let me say that I'd like to kind of use this talk to put all of the work in a sense of, in memory of Wei Wilbur Shi, who had been, I've been lucky to have him in my group for about 2 years, probably more than 2. And some of his work has actually been quite extraordinary, and I'll mention some of his contributions down the road. And these are the 2 pictures that I could find on a Facebook or actually digging through the internet. Sorry for that, I'm going backwards. So the problem that we kind of looked long time back had to do with solving a minimization convex problem where we basically, we don't assume any constraints in this problem. We are minimizing the sum of the functions, and the main change in the problem setting was that we considered the situation where the functions are actually associated with the different agents in a network. So for the most of the time, I'll be focusing on a simple network, which is, let's say, undirected, and it has basically the network identifies a communication structure that's underlining, and the agents have, every agent in the network has its own objective cost function. The functions are also for the most of the talk assumed to be convex and differentiable, even though you can extend it beyond the basic convexity and differentiability. And the main part is main kind of a change in the because this problem, if you had all the objective functions at some central entity, you could easily solve. There's nothing new about it. So the change was that we would like to solve this problem while imposing constraint that every node, actually the agents that we refer to them kind of interchangeably, has an objective function that is only known to that agent. And as I mentioned, so each of these functions will be convex and differentiable. And the agents need to solve this optimization problem while they can leverage actually the presence of the network that allows them to communicate. And the main, another assumption is that the agents are not at any they're not allowed, or for privacy reason, they don't want to exchange the functions. So they are not going to share the functions to the neighbors. So to solve this problem, we came up without the central entity. Basically, there is no coordinator that is going to coordinate computations in these graphs. We kind of considered a possibility to use some kind of consensus models as a virtual coordinator. And here, I'm not going to kind of go through the list, but there are some basic papers that we actually, the most influential for the work we started was really this thesis of Tsiklis in 1904, that gave us a lot of kind of insights about how you can use the consensus to act as a virtual coordinator for this computational model. And some of the examples I'm going to mention here is, I have to be also in a full disclosure, these examples about applications came years later. When we were beginning to work on this model, our simplest kind of application we could think of was the sensory networks. But these days, it turns out it could, this framework is quite useful for kind of machine learning problems. And some of my students have considered these applications. And I'm here, you can see their names. This was probably 7-8 years ago, Kunal and Sumin. They were looking at the machine learning coming, actually specifically problems when you have the data. So at every node, you have a collection of the data so that individual kind of objective function at a given node is reflective of the data points, which are really captured here by some loss function. X is a common vector. It's a decision vector that they need to optimize with respect to. And the Z's and Y's are kind of data points in the labels. And usually in these problems, you also have a common kind of regularizers, which kind of can kind of impose specific properties on the kind of in the problems of a linear separator, like this problem that we are really looking here. Rho is more of a function that specifies additional properties of the solution you want to look at. For example, you can impose like sparsity, and usually the Euclidean norm is used, but in some situations you might impose L1 or as an approximation for the sparsity requirements. And as a simple example of a loss function, you might consider so-called the logistic regression, and so on. And actually, we have looked at other options for applications, such as with one of my actually first PhD students, Sunhar. He looked at the uplink power scheduling, and more recently with one of my the most recent graduate students, Caesar. He was looking at hypothesis testing, where these functions here, regularizer doesn't exist, but these functions assume something that is motivated by Bayesian kind of updates. Anyhow, so let's go to the next page. Sorry, I will have a problem with coordinating this a little bit. So just to go back, so now you can imagine any of these functions and any of the applications you would like, but we'd like now to kind of take a look at the network side. So I will, for the rest of the talk, assume that there are M agents. So the node set is M, and the edge set is just basically represented by some undirected links. And the main assumption that we're going to use is this graph is connected. So one option is to kind of, if you want to reformulate this problem, it's a simple thing, is to just recast the problem to capture the fact that there is a network. You can reformulate it by saying, okay, we can just decouple the agents, but saying, suppose every agent has its own decision variable, and then encode the kind of network kind of embedding in a sort of saying who can talk to who. We can impose by saying the decisions of the agents that are in the graph, and basically saying that for every agent I, we can impose that that agent has to have the same decision as any of its neighbors. And we refer to these constraints as agreement constraints, because they are really forcing the kind of artificially forcing that the variables have to agree. And when the graph is connected, this kind of results in basically saying that all of the agents will have the same decisions. So from that point on, we can really view the original problem as really constrained problem in this manner, where the objectives are basically separable, but the coupling of the agents comes from the basically these constraints imposed by the network that dictates who can talk to who. And then in this particular setting, if you set up these objective functions to be 0, you're going to recover a problem that's known as agreement problem. When you are really looking, it's called, you can think of it, it's really a feasibility problem. So the objective here becomes 0. And in that feasibility problem, all you are asking is that the agents agree on a variable, on the same value. That's really this constraints impose that. So when you look now in the literature that allows for this agreement problem to be solved, actually there are many, I realized that word consensus means different things to different people. There are various ways to achieve consensus on a graph. You can use the minimum or the maximum, but that's not what really we usually use here. When we think of consensus problem, we really think of some iterative process that can lead to asymptotically, that if you run this iterative process in the kind of into infinity, you will obtain a common value on which the agents will agree. As I said, you can come up with other processes that may compute maybe the minimum or the maximum of the values of the agents that they have initially, but that's not going to help you solve this optimization problem. So for the purpose of aiming at solving this kind of joint optimization problem over graph, it turns out that processes that I'm going to call them weighted averaging will actually be useful. And I'm apologizing to those who are familiar and probably deeply involved in the research of this, but I'm kind of aiming at to reach to those that may be hearing this kind of for the first time. So one of the possibilities to solve this consensus problem is by utilizing the equation that you see at the end of this slide, which says that agents will at time t exchange their, using the links that are available in the graph, they're going to exchange the information about their most recent decision variable, which is denoted by xj of t. So every agent j sends xj of t to the neighbors. And then node I here will receive these values from the neighbors. So this n sub I identifies the neighbors of the agent I. And also the agent I will take into account his or hers own decision xi, and the values that are received from the neighbors and its own value for the agent I are weighted here by some values aij, which are assumed to be positive. And they also satisfy this constraint that the values are summing to 1, which is why we refer to them as a convex combinations or weighted averaging. Now, to kind of simply look at this process, to understand what such process would do, you can augment these weights by setting up these weight values to 0 when the links don't exist. So for the all j's that are not the neighbor of I, you set these values to 0, and also for the II kind of self loop that you're creating here, AII is also 0. And if you rewrite this process in terms of this matrix that you can define based on the graph and the connectivity, it's relatively easy to see that this evolution of the process is really linear. It's dictated by the matrix A, and you can capture the evolution actually all the way through the initial point, and you find that the matrix A to the power t plus 1 is responsible for the behavior of the values of these x variables. Sorry, I skipped too fast. And another kind of influence comes from the initial states of these initial values of that agents are holding at time 0. So it happens that when the matrix A is row stochastic, and that's exactly the case when these weights are summing to 1, that's row stochastic means exactly convex combinations in terms of the weights in the rows. Then the limiting matrix, the matrix A to the power t will converge to some, to very kind of, will have a limit. And the limit is determined by this kind of expression where what this expression says that in the limit, these powers converge to a matrix which has a rank 1 and all rows all rows have the same values which are given by this vector pi. Vector pi is a stochastic, which means its entries sum up to 1. And in this case, there's more to it. Actually, all the values of this vector pi are positive. So one can, from using this limit matrix, one can actually come up with an exact expression. If we know the vector pi, then the limit for this consensus process, every agent will converge to the same convex combination of the original values of the agents. So it turns out that this kind of, even though consensus problem itself solves just this kind of agreement, it turns out that combination of this consensus kind of process with an optimization algorithm can allow you to solve the problem that we originally posed, kind of distributed problem of optimizing the sum of the objective functions over the network. And originally we came up with this very, very simple model which mimics the gradient descent by saying, if I want to solve the optimization problem, what I can do at a given time t, I will exchange my decision variables with my neighbors. So if I'm agent I, I'm going to receive the values from my neighbors, and this aij is 0 if my agent j is not my neighbor. And then in this step, we just mimic what the gradient method does. And it's very simple. It says I'm just going to take the step size along my own gradient. If I'm agent I only know the function fi. I know my current estimate, which is xi of t, and I'm just going to move along. A few years later, one of my students came up with a kind of a little bit better version of this model, which says, okay, if we are mixing here the decision variables, why are we not computing the gradient of the objective function at the same updated kind of using this most recent update from all the neighbors. So these basically algorithms, they're almost the same in terms of the asymptotic behavior, but this second version is somewhat kind of more friendly in terms of the analysis. You can get a better bounds. In terms of expressions are easier to derive, but in the limit asymptotically, there's not much difference between the two. And then regarding the method, one can show that if the graph is connected, if the matrix here has to be doubly stochastic, and I'll return to the point why we needed doubly stochastic. And I'm now assuming some very simple, I'm keeping this situation very simple so that the gradients are assumed to be bounded. Step size is satisfying the standard conditions that you would find in, if you're using diminishing step size, this infinite travel path, the first condition, and the square of the step size is being summable, basic assumptions if you want the gradient method to work, without assuming any other properties of the gradient, basically not requiring Lipschitz or any other properties. And it turns out that this consensus mixing with the gradients allows you to prove under this step size, which is coordinated here, one can note, that every agent will converge to the same limit point, which is X star, and X star is actually solving the problem. The convergence rates are kind of comparable to an extent, I would say, with the log term extra, if you were considering the same method in the absence, in the case of the centralized. So you use centralized gradient to solve the problem, you would get all of 1 over square root of t if you're doing it centrally. But because of the decentralization, we are kind of incurring an extra log t term here. And for the strong convex case, the similar story goes. You in the centralized case, you would have a rate of 1 over t, while in the absence, due to the, again, mixing and this consensus kind of interference, you're gonna lose log t. You're gonna incur extra log t power. So now the part here is that I gave you a simple result, but result is extendable, and I just didn't want to go into those details. You can extend it to the case when the graph is time varying, and you can even stretch the connectivity of the graph. Instead of instantaneous connectivity, you can ask for connectivity that's delayed, but there is an upper bound on how long you can allow the graphs not to be connected. But the key part is that all of these matrices that are used in the kind of mixing, now they will depend on the graph, but they have to be doubly stochastic. And we recently had a work when our original work didn't really account for how these matrices change, and what can you say if you knew, or if you impose some additional constraints about how these matrices change, what can you say about the rate? So there was a recent work by one of the students at MIPT in Moscow, who actually went to some tedious analysis to analyze the behavior on the algorithm, assuming some slow change in the graphs. And there is actually this paper has been just recently accepted. Bottom line of the problem is, of this kind of approach, is that the method is kind of slow. That's one of the main characteristics, because it does depend on a diminishing step size. And once you use the diminishing step size, you are kind of, convergence is kind of constrained with the behavior of the step size. That's additional side. So the first thing I want to return to is that why we needed double stochasticity. For this setting, it turns out, meaning it's byproduct of the analysis, that if you use arbitrary stochastic matrices here, then what you end up solving is this minimization problem, where vector pi is this so-called fiddler vector. It's the left eigenvector associated with the eigenvalue 1 of this row stochastic matrix. So this is that's what equation-wise I mean. So if your matrix is only row stochastic, this vector pi is well defined under the connectivity assumption, and you will end up doing minimizing this problem. Intuition comes from really interpretation of this matrix as a Markov chain matrix, matrix that represents the transitions of the Markov chain. So in the limit, these pi's are basically a frequency with which agents are pushing the information about their function into the network. So you end up minimizing this kind of expected value of the function. And when so if you want to solve the original problem, you would like these pi i's to be the same. And that's going to happen if your matrix A, for example, is doubly stochastic. I am not aware of maybe there are other matrices that are going to allow you to do that, especially when you're allowing these matrices to be time varying. But in kind of limited with our own knowledge, we just resorted to doubly stochastic matrices. And the second thing, so aside from one criticism that the algorithm is slow because the step size is diminishing, another kind of pretty rigid kind of drawback of the algorithm is that if your graph, so we kind of look at undirected graphs, but if you look at the directed graphs, then coming up with these doubly stochastic matrices is going to be it's going to be expensive because you have when the graph is bidirected or undirected, whichever expression you like, you can construct these matrices to be doubly stochastic on the go, even if the graph is changing. You may need to exchange a little more information, but it's doable. But if the graph is directed, then there is no way to do it in a kind of pre-iteration. It turns out that somehow you may need to run an additional process that's going to do that for you, but that's not the direction we wanted to go. So we kind of looked at additional possibilities of, if your graph is directed, how else you can replace consensus update, because that's the step that depends, that was the critical for information exchange. How would you replace that step now with something that is doable on a directed graph? And we actually, about that time, there was a work by Konstantinos Tsianos. He was at the time student of Mike Rabat, and they came up with one of the first algorithms but they exploited, I don't know who's aware of that, this dual approach proposed by Nesterov, which is really kind of everything is happening in the gradient space. And once they did that, it caught our attention. So we kind of developed some work, and I'm not going to talk too much about that one, but we have basically developed a couple papers, I think, with Alex we worked on that side saying, okay, what can we do if the graph is directed? Next, that I would like to more focus, and that's really what I'm aiming toward the end of the talk, is to say there are the more important to us was that the fact that algorithm is slow. So that if you have diminishing step size, you're done, meaning that defines your rate. And then attention to us was drawn by Shi, Ling, Wu, and actually Wilbur, who created this extra algorithm, and in the aim of accelerating the method on a static graph. So what they kind of put forward and makes complete sense is the saying that if you want to accelerate the algorithm, the only way, meaning the only way we know how is you have to fix the step size. So you think what's going to be, if you have a convex problems and you're solving them in general with the gradient method, what's the fastest thing you can possibly get? Well, you get the geometric rate under the right conditions on the objective function, but to do that, your step size has to be fixed. You cannot go with a diminishing step size and achieve the best performance. So if you plug the constant step size in our algorithm, a most likely algorithm won't converge, but if it would converge, assume it does, just for a kind of mental experiment, then it turns out that, roughly saying, what happens is that in this equation, you just let these xi of t's converge to some number, and you explore what's happening, what kind of limiting point you can possibly get. By plugging that, it turns out that if the algorithm would converge with a step size that's fixed, it would imply that in the limit point that the algorithm would reach, all the gradients of the agent's objective functions would have to be equal to 0. That's kind of what it's saying is that the problem that you are looking at, there must be a common solution or a common minimum to all of the objective functions. And that was not really a good news, because we don't want to look at just these problems. That was not the purpose. That was not the problem we wanted to solve. So that was our kind of bottleneck. So we said, okay, let's look back. Let's look back at the problem. So you are looking again back to this problem when you are minimizing the objective function, which are really, objective function is really decoupled variables individual to the agents, but you are also having, but the agreement constraints are kind of subject to these agreement constraints that are arising from the network structure. So the option, when the graph is fixed, alternative is just to look at this problem and apply dual algorithms, because you can dualize these constraints and resort to solving the duals. And we have looked at that approach, again, recently got published, but you can basically in this, through the dual approach, you can match the performance of fastest algorithms in the fastest centralized algorithms up to a log factor. Again, we are hitting this log factor due to the mixing, because there are these constraints and consensus process creating this log factor. But the problem is that this approach that we looked at does not allow you to handle the case when graph is dynamic. This allows us to address the problem when the graph is static. It requires some assumptions and some knowledge that maybe it's actually could be quite demanding even if the graph is static. And the worst case was actually we could not extend it to the time varying graphs. And Rogozin, this paper that I mentioned at the very beginning, he manages to do that, assuming some conditions on how the graphs are changing. And we refer to that slowly time varying. But in general, if the graphs are just changing and the changes are not slow, we cannot address this problem. We were not able to accelerate by using this dual approach. So next step would be, okay, let's go back again to the drawing table and let's see what are we doing in this distributed setting. So it turns out what is the algorithm was doing is like mixing agents exchanging the gradient, not the gradients, exchanging the decisions and mixing the decisions. But in terms of the update, when the objective function was accounted for, every agent was quite selfish. It was just using its own gradient, whether it was evaluating its most recent decision or mixed decision, it doesn't matter. It's a pretty selfish behavior. So we thought is that while agents are collaborating on the decisions, they absolutely do not collaborate on the direction. So the first kind of instinct would say, why don't make the agents also more aware, since they're aware that they are part of the system and they are collaborating on the decision, why don't we make them aware of the fact that they're also solving an objective function and it's not just their own. There are other agents that have different objectives, and the selfish step has to be adjusted to understand there is something, that there is a system level objective. And one option to do that is to, just like you are tracking the decision, when you call it here collaborative decision, you can consider tracking something that is hopefully in the long run would be an estimate of the gradient of the system objective, and that's this GI of T. So it's a estimate of what the gradient the gradient of the system objective might be at the time T. And this kind of estimated gradient is updated in our initial kind of, let's say, first look at algorithm that possibly uses such an estimate, may also, when the graph is fixed, use the same weights that you are using to mix the decisions. You can consider using the same weights to update your direction. So in this case, agents would exchange not just their decision, but also their estimates of the gradients. So every agent J that's a number of I, would send the information about the gradient. We mix them similarly the way we mix the decisions. But there is additional step here, which is saying upon mixing, every agent I would also into this update account for this difference between the gradient evaluated at the most recent update, which is at the time xi of t plus 1, and subtract the most recent gradient that it used in the prior iteration. So this step is quite important. It's kind of different from the decision because what it does, this particular here term would kind of, you can think of it, if you have seen Kalman filter, you can think of it as an innovation term. So it just brings into the combination, kind of adds into the update, only the difference that comes from the new update and tries to filter out the old information that's already encoded into this direction GI. And here the step size is fixed. So this looks a lot like tracking. And in that terms, we actually, the ideas initially we got had to do with some form of similar approach that was used by Zhu and Martinez, but they did something different in the paper, in this paper here. Then also we saw similar idea in Jinming Zhu's kind of thesis. It was, I think, yeah, PhD thesis, that he's using similar tracking, but for augmented distributed gradient methods. And also at the same time, which we learn later, Aldo was doing actually exploring this tracking and using it, and has developed actually several papers here that different algorithms come with different kind of acronyms, but in principle, the same idea of gradient tracking comes from Aldo's group. And well, here is, I don't know, Aldo, there's probably more recent. This is, I lost the track for the last year. But so what is bottom line? Now you can think of extending this same algorithm to the kind of situation where the graphs are time varying. So that's why now I'm assuming the graphs are undirected. They might be time varying. So we are just here showing you the same algorithm in the case when the only change is that these matrices now maybe depend on time. and they are still reflective. Again, the weights are 0 if the agents are not neighbors of each other. Otherwise, the weights are positive. And if we want to address the case when the graphs are time varying, we are assuming that there are some additional assumptions. I'll come to them in a minute, but the weights are also assumed to be doubly stochastic. Compatible with the graph just means that diagonals of these matrices are positive, and there are positive weights on the neighbors. Basically, that's it here. Step size is also assumed to be common to all. So somehow we pre-code the step size to all of them. And then we start the initialization is a bit not tricky, but requires some care. Agents can start their Sorry? Sorry?
No problem. I think just someone forgot to mute themselves.
Oh, that's fine.
Just a reminder also that this is we only have maybe 5 minutes left.
Oh gosh, okay, I'm gonna have to fly.
I mean, just please feel free to. I mean, you can over the 10.
I can see that. So the key point here is that these gradients have to be locally computed at a particular way. So let me get it out. So bottom line, this algorithm, I'm gonna skip these assumptions here. We can, if you want to chat offline, we can do it later. But it turns out that with this tracking kind of mechanism, we were able, this is actually work by Wei Shi. Wilbur did this analysis, it's pretty nasty. And he shows that this tracking algorithm can achieve, agents will achieve consensus, agree on an optimal value of the problem, and the rate at which they are going to get there is really geometric, and it requires under certain assumptions. So you need functions to be some of the functions need to be strongly convex individually. Every function has to have a Lipschitz gradients, and kind of analysis, meaning this is just one snapshot of one option. If you're looking at perhaps, let's say you want to be kind of concerned with how this algorithm will depend on the network size. There are some specific results here that are trying to pull out the estimates in terms of the number of agents. Bottom line, that again, I want to say, I don't think our bounds were very, I believe our bounds are rather loose. We do have a theoretical kind of selection of the step size, but it requires knowledge of the graphs. It requires some structure. So I would consider it as a very theoretical result. I'm not sure how practical it is, at least not in the version we got it. So the more recent work has actually come within the last maybe 2 years with one more postdoc that I had, and it was also developed by Wilbur, Jinming Xu, and Shipu. So they realized that there are, in this tracking algorithm, there are some variabilities that we can implement. And we started with a static graph in which you may try to do something. Let me see if I can go to the next slide, which basically says, it's kind of building on. It says you may consider a variation of the algorithm where in the updates of the decisions, you may use a row stochastic matrices. But when you all go for the updates of the directions, you may not necessarily use the same matrix. Originally, we used the same matrix in both updates. They came up with a variant when you can use a different update here. And this matrix, actually, what you want from the B matrix is to follow some kind of graph structure. But this matrix B needs to be column stochastic. So let me again fly. So there was some, actually in this kind of direction, we have came up with something that in Usman Khan's group was developed about the same time with one of, I think his master student at the time, Ren Jin. And we kind of put the forces together later on. Bottom line, I'm not going to be able to discuss this. It has to, this algorithm, originally we call it push-pull, but seeing the work at Usman's group, we kind of noted, we call it AB push-pull, to kind of have it something that is kind of representative of the work in both groups. And these lines here, it just kind of gives you, I'm not going to be able to go through the details, but it kind of provides some form of intuition of why the algorithm of that form would work. And the bottom line is that connection is really, when you look at this model and the optimality conditions for this problem, you can come up with the relatively simple conditions under which optimality conditions of this problem and the limit points of the algorithm in the prior kind of slide kind of in asynchrony. So your algorithm really solves the optimality conditions which are reflective in this last bullet. And I'm giving you here the case when you're solving a scalar case to just make the kind of, instead of going into matrix formulations, this just stays on the vector formulation. So it turns out that this algorithm now that we call AB push-pull also can solve the kind of original problem we casted in the first slide. It can be done sufficiently exponentially fast, exponentially. It's really a linear rate or geometric, depends on the language you use. And also we have results that are also discussing kind of ranges of the step sizes. And this approach is, okay, to analyze the algorithm kind of trick is, and she did a great analysis, but he kind of buried in the proof, there were 3 values that you need to check. You are tracking the behavior of the average, and this average here is not the regular average. It's a weighted average that depends on this left vector of the matrix A, the Frobenius vector. You're also tracking how your iterates differ from that average using the same kind of weighted norm here. And third item you track has to do with how these directions that the agents are using are behaving with respect to something that's kind of a common direction, scale direction, but depends on the a vector that is associated with this mixing matrix B. The analysis is rather tricky, but the bottom line is you provide something that looks like this. For all of the quantities, you provide behavior in terms of one state transition. And then the key work and the actually hardest part is really analyzing of this matrix, which is governing this inequality. And this is to be understood in terms of these are vectors. So the inequality is really component-wise. The matrix, I'm summarizing it here, what it looks like. It has terms that depend on the step size, order, first order, and also on the second largest eigenvalue, the singular value of the matrix A and the similar for the B. And then it turns, when you're providing these step size ranges, you really, what you're doing, you are forcing this matrix D to have a radius, this spectral radius less than 1. So that's the kind of, on a simplest possible way to explain what the analysis is doing. And kind of, you can find some of the detail. Actually, this particular approach, I found it very nicely given in a paper by Shin, Sahu, Khan, and Carr in the prior CDC, even though they did consider a stochastic variant of the algorithm, but the key part is really this kind of 2 lines that I make them very simple, but there's quite a lot going on in between. And then we recently kind of have a survey paper in which we are looking through this push-pull, A-B push-pull. You can recover in various combinations a lot of algorithms that have been done. And among them is also Frost, which was done by Marie Maros. I saw you, Marie, there. So that's very recent, but I gotta admit, it's really work by Shin and Pu. I was just on a side. And with this, I'm gonna just kind of summarize in 1 minute. What we have done, we moved from something that was very simple, very kind of myopic, to move into the direction of speeding up, trying to get the algorithms to work as fast if they were centralized. But there are several other directions in which people have been looked at. There have been attempts to look at convex problems, and there are some initial works by Tanya and Behruz. Aldo had done quite a lot. Actually, his whole quest on these algorithms started with something that is very, very general and addresses the non-convex problems. And I got recently a paper by Shahin Shahrabur, who's also looking at this non-convex issue, but I haven't read it. But I'm citing it here because I see they are doing something distributedly for non-convex problems. There is also asynchronous implementations, which we haven't really done as much. Network topology, how it impacts the behavior. Delays is one of the main issues, and Michael Johansson and Rabat have been doing quite a bit on that end. Behavior of these algorithms, if you have malicious agents, has also kind of attracted attention. And I know To, you've been looking at that with Manoush, Sunaram at Purdue, Anna, Vaidya, and even also Wahid had been looking at that. And one of the other aspects that people have just maybe within the last few years, considering how do you make these computations private? But it's not a privacy as people consider often in this setting, whether they call it a differential privacy. Depends what you want to keep private. In this case, you want to keep your computations private and sort of you want to keep the gradients in a, you don't want your neighbors to be able to pinpoint and identify what your objective is. So Yongkyang Wang at Clemson is doing some kind of dynamic-based privacy, which is addressing those issues. And with this, I have to stop. I have ran probably over the time, and I want to thank you, and I'm here to hear your questions.
Okay, so so first, I think I would like to ask the audience if you have any questions. I mean, since we don't have many questions here, so maybe you can just unmute yourself and ask. So maybe I can start with the first one. So so you mentioned about this geometric convergence weights of distributed algorithms, and so I'm wondering, like, have we seen any works that actually does something even better than linear weights, let's say superlinear in distributed?
Yes. Yeah. Oh, sure. Sorry, I don't want to change the share. Yes. Okay. Let me back off. I haven't seen it in this distributed setting. In the way, what I'm referring here is that, but I could see you can use this tracking to do maybe Newton method. But there is a catch. So here is where the catch is. You have two pieces, consensus. So think of the optimization side versus consensus side. So in the optimization side, let's say this beautiful convex case, everything is nice. You can use Newton method and you can have a very fast behavior. consensus, the way we are using it in both variants, meaning whether you have directed or undirected graphs, doesn't matter. Consensus is kind of stuck to a linear rate.
Yeah.
So if you merge the two, there is no hope you can do better than linear.
Yep.
So the bottom line seems to me that the only speed up further we can get is perhaps if we have a faster algorithm for consensus. So if I can get that one to be super linear, then I can try to match the two.
Yeah. Yeah. I mean, that's also what I think as well. But I haven't found any work that is going on this direction yet.
Yeah. So I guess
that's very interesting. Yeah.
Yeah, the hard part will come from, you can cast the problem, like, let me see if I can move through these slides, not as easily. Here it is. So the problematic part is the network.
Yeah.
Because you can cast this problem, this constraints here as a linear constraints. But how would you, the problem is if I want to speed up with solving those constraints using Newtons, I have to exchange information that's not just local. And I think that's what the bottom line is. It doesn't mean it's not doable, but we haven't done it yet.
Yeah, that's interesting. Yeah. So is there any other question from the audiences? I mean, feel free to speak up. Okay.
I can stop sharing.
Yeah, it's okay. So let me check the chat box. We don't have anything yet here.
It's either too early or too late.
It's actually quite a convenient time for us at the moment. It's only 11 a.m.
Oh.
Yeah. Oh. So there's a question from Tiani. So the question is about whether there's any work about adaptive step size in decentralized settings.
I have not seen it.
Yeah, I think that would be, wouldn't that be related to something like asynchronous step size that, I mean, this is also one of the work from Wilbur.
Oh gosh, yeah. Wilbur has done, although it's a short paper, he had extended with Caesar that I'm sorry, maybe you have been involved in that paper too.
No, I wasn't. I was just discussing with them at that time.
Yeah, because what happens is that they came up with a version of this algorithm where you don't have to use same step size for every agent. Every agent can decide on their individual step size based on the local information. That's the only thing we have. But adaptive is something that I would think, what people would think usually is like, depending on the problem, yes, I may decide to change the step size. Let's say you keep it constant for a while. You adaptive means you decide when you're gonna drop it, or you have criteria how you're gonna choose it. I haven't seen that. That doesn't mean people may. Yeah.
So that's actually a reply from Lin Qin. So he said there's actually some recent works using Adam like adaptive step sizes to train DNN in a stochastic decentralized manner. Yeah. So yeah, I mean, I guess we can actually go into those literature to check how they're available.
Yes.
I know there are too many of them.
Yeah, and the part is that, okay, I have not seen it, but that there is a pointer where one may look at it. There's another question that I see, with the momentum type methods be applicable. Actually, Usman Khan in his group, and I don't know, I just remember his name. I don't know if Ren Jin was involved.
Yeah.
They have looked at some momentum type, which is, they looked at Polyak type momentum, which means you look at the sort of convex combination of your most recent iterate and the difference between that one and the step behind. So you have like two memories, two steps. But I have not seen a Nesterov, because Nesterov is a bit trickier for analysis, much trickier. So I haven't seen Nesterov acceleration, but this momentum type, kind of Polyak type, yes. Yes, yes. But Lina group has looked at it, but I think it has it's a bit trickier because you still need quite a lot of synchronization there. If you think of the Polyak step, Nesterov acceleration term, it's rigid. But yes, I agree. I forgot that. Lina, yes. Lina had done that with, what's his name?
Chen Nan. Yeah.
Yes. With him. Yeah. They have a paper, one paper on that.
So there's also a question from Mingze. So is there any work about analyzing the convergence of gradient tracking with quantizations and compression? Definitely.
Not that I know of.
Yeah, I mean, maybe I can contribute something here. So there is actually recently quite a few works from a group in EPFL from Professor Martin Yagi. So they have done something with quantization, with gradient, not necessarily in the context of gradient tracking, but decentralized optimization in general.
Okay.
So yeah, so they have this this thing they call error compensated distributed gradient descent, this kind of thing.
Okay, that's I'm unaware of that. I haven't seen it. I know there have been work a lot on the consensus side with the quantization at some time. Maybe not that much lately. Maybe 5-6 years ago is the latest one I've seen. But that's what the art of the, I think, guys who do the wireless information theory and things like that. No, I haven't. Okay, that's meaning I'm learning things. I'm not seen it.
No, we're learning from you.
Because the bottom line is the meaning assumptions we are making is like how are not realistic, because when we say memory of one, I still assume you're storing the entire real number, and that's where these things are going, because in reality, no system stores the entire one real number. It does have to, effects of quantizations, they have to be, they're gonna add another layer of errors.
Yeah, so I think the idea they used in those error compensator algorithms is like, so instead of quantizing the gradient that you're sending over the network, you're quantizing the differences of the gradients. So then you do some kind of error compensations, very similar idea like gradient tracking in my opinion. So I think actually Shipu also did something like this in his recent CDC paper.
Is it CDC this year or the next?
Yeah, it's the CDC this year. The one that is happening right now.
I'm not there. Not virtually nor physically. No.
Yeah.
No, I can check that.
Yeah. I mean, we can talk more about this later. So I guess there's no further questions, and I believe that it's probably late for some of you. I mean, especially those in the US. So let's join me to thank the speaker again, and let's conclude with the talk today.
Thank you.
And thanks for attending this one-rail signal processing seminar. This is going to be the last one for year 2020. And unfortunately, we haven't been able to meet each other in person throughout the year. And hopefully we can do so next year.
I hope so too. I do. And thank you. I wish you a happy new year, and I hope we get out of the COVID.
Yep, indeed.
That's all I wish for.
Okay.
Thank you, Angelia.
Take care. Thank you so much. Thank you.
So, Shao, can you stop the recording?
Sure.